Welcome to our quantum deep dive. Today we're plunging into the really profound world of quantum physics. We're doing it through the lens of a truly revolutionary scientist, Lene Hau. We're drawing our insights today from an illuminating essay by Vestergaard, which traces her incredible journey and, well, the groundbreaking impact of her work.
Yeah, and our mission for you today is really to unravel how Lene Hau didn't just, understand light and matter in the old ways. She fundamentally redefined them. She made what once seemed utterly impossible, well, a tangible reality. So we're going to explore the monumental implications of her discoveries, everything from the bleeding edge of quantum computing right through to transformative applications in medicine. Get ready for some genuine aha moments, I think. It might shift your perspective on the universe a little.
Okay, let's unpack this. Lene Hau's remarkable story starts in Velo, Denmark. Apparently, from a young age, she had this extraordinary interest in the natural sciences, particularly physics and maths.
Right, and it wasn't just like a casual childhood curiosity. The essay points out it was a really deeply ingrained fascination with fundamental things like light and gravity. That foundational drive propelled her towards academic excellence and, ultimately her place in science history.
What's really significant, I think, about her early academic journey was her path at Aarhus University. She initially went into mathematics, right, drawn by its logic and precision.
Exactly. But her passion quickly pivoted to physics. She saw the potential, the exhilarating potential, to apply those complex mathematical concepts to understand and maybe even manipulate real-world phenomena. It was there she really discovered her deep affinity for quantum mechanics, inspired by giants like Niels Bohr and Schrödinger.
And Schneepatz's essay highlights this pivotal moment during her studies, her involvement in an atom physics project. This introduced her to something called ultracold materia, ultracold matter. That phrase alone sounds like something out of sci-fi. But what exactly is ultracold matter?
Yeah, it does sound futuristic, doesn't it? And this project was crucial because it directly paved the way for her specialization in atom optics, and her later really groundbreaking work with Bose-Einstein condensates, or BECs.
BECs, right.
So ultracold matter, put simply, it refers to atoms cooled to temperatures incredibly close to absolute zero, minus 273.15 Celsius. And in that state, they exhibit these highly unusual collective quantum mechanical behaviors.
Behaviors.
Yeah, it's almost like they stop acting as individual particles and begin to move and interact as a single coherent superatom. It's bizarre.
Oh, wow.
So understanding and creating these extreme states, that foundation, is what ultimately led her to Harvard. That's where her most famous experiments started to unfold.
Okay, this brings us to Harvard, because this is where it gets truly mind-bending, as you said. Hau embarked on this revolutionary hypothesis. Could light, that universal constant zipping along at almost 300,000 kilometers per second, could it actually be manipulated? Could it be slowed down?
Yeah, it sounds completely counterintuitive.
Absolutely. To everything we learned about physics, what was she challenging there?
Well, you've hit the core challenge. Classical physics, even Einstein's relativity, treats the speed of light in a vacuum as this immutable constant, c. Hau's work didn't contradict that constant exactly. It explored how light behaves when it's not in a vacuum, but interacting with some kind of exotic medium.
Ah, okay. The medium is key.
Precisely. Her main focus was on how light interacts with those ultracold atomen, specifically those Bose-Einstein condensates we just mentioned. She saw these BECs where atoms achieve this state of quantum mechanical coherence, meaning all their quantum properties are perfectly synchronized, entangled.
Right.
She saw that as her key. She thought this collective coherent state could serve as a unique optical medium to influence light in totally new ways. It was about leveraging the quantum nature of matter itself to sort of, bend the rules we thought were fixed.
And bend them she did. In 1999, her team just stunned the scientific world. They managed to reduce the speed of light from nearly 300,000 kilometers per second down to, 17 meters per second.
18, yeah.
Just think about that. That's slower than a bicycle, slower than you or I could run. It's almost unimaginable.
It really is. That analogy of the bicycle just drives home how huge this was.
So how? How did they pull off the seemingly impossible feat? You mentioned BECs and electromagnetically induced transparency, EIT.
Right, EIT. It sounds like a mouthful, but that's the key mechanism along with the BEC. So they used a BEC made of ultra-cold rubidium atoms as that special optical medium. Then, through incredibly precise laser control, they leveraged both the quantum coherence of the BEC and this EIT phenomenon.
Okay, break down EIT for us a bit.
Okay, so EIT is essentially a quantum optical effect. Imagine a material that normally absorbs a certain frequency of light. It's opaque. But if you shine a second, precisely tuned coupling laser on it at the same time, that material can suddenly become transparent to the first light.
Like making a window appear.
Sort of. It's like creating a temporary quantum window, or maybe a detour within the BEC. This effectively pauses the light's journey. It does this by temporarily absorbing the light pulse's energy and information into the collective quantum state of the atoms in the BEC. Then it re-emits it later. So the light isn't physically traveling slower through space between the atoms.
Oh, okay.
Its energy and information are being transferred into the atoms, held or stored for a moment, and then transferred back into a photon. But that whole process takes time, which results in this appearance of a vastly reduced overall speed.
That's incredible. So it's not just crawling along. Its essence, its information is being absorbed and then released. And what's even more mind-bending, as Schneppat details in the essay, is that Hau's team later managed not just to slow light, but to stop it.
Completely.
Exactly. That was the next giant leap.
How did that work, and what did that represent conceptually? Stopping light. Well, they refined the technique. They essentially imprinted the light pulse's photon energy and its quantum information fully into the collective quantum state of the BEC atoms. Think of it like pausing a video and storing all its frames, but quantumly. The light pulse ceased to exist as light for a fraction of a second.
Wow.
And then, the incredible part, they could release it again on demand by turning the coupling laser back on. It reconstituted the light pulse perfectly, with its original information intact.
Unbelievable.
This wasn't just a technical feat. It fundamentally challenged that classical idea of light as this immutable thing that's always moving. It proved light could be, well, interrogated. Its information could be extracted, held in matter, and then returned. It blurred the lines between energy and matter in a way few had dared to imagine. This concept of light as a storable unit became a reality.
Light as a storable unit. That's paradigm shifting. It challenges the idea of light being separate, untouchable from matter. Okay, so this is amazing physics. But what does it mean for us? For everyday people? Maybe not today, but down the line? This isn't just a cool lab trick. Hau's work has these profound implications for cutting-edge tech. Let's start with quantum communication and storage.
Yeah, it connects directly. What's fascinating here is that this ability to store and release light pulses in matter is absolutely fundamental for developing practical quantum memories. And you need quantum memories for secure quantum information exchange, for building truly global, unhackable communication networks.
Unhackable communication, like quantum key distribution, QKD.
Exactly like QKD. That relies on the laws of quantum mechanics. Any attempt to eavesdrop inevitably disturbs the quantum state, alerting the users. It's inherently secure, not just hard to crack.
A game changer for security.
Absolutely. And think about building a global quantum internet. You need quantum repeaters to send fragile quantum information over long distances without losing it. Those repeaters rely heavily on this ability to store, process, and re-emit quantum states encoded in light. Hau's work is foundational there.
Okay, and what about quantum computing? We hear so much about that potential revolution.
Her work laid crucial groundwork there, too. For storing and manipulating qubits, the quantum version of classical bits.
Right. Qubits can be 0 and 1 at the same time, superposition.
Exactly. And the ability to temporarily store light's quantum information in matter is key to holding these incredibly delicate quantum states long enough to actually perform computations on them. It enables more efficient quantum gate operations, the basic building blocks of quantum algorithms, and, maybe even more importantly, it paves the way for error correction in quantum computers. Quantum states are super fragile, errors creep in easily. You need ways to store information robustly while you correct errors.
Which is critical for making them scalable and reliable.
Absolutely critical. Moving beyond small prototypes to machines that can solve truly complex problems.
But her influence isn't just information tech, is it? It sounds like her work in manipulating atoms with light has broader ripple effects.
No, definitely. Her innovations in what we call atom optics, using precisely controlled light to manipulate atoms, breaking them, stopping them, even reversing their movement, that led to entirely new experimental methods, things like optical traps or optical tweezers.
Using light to hold atoms.
Yeah, focused laser beams hold and cool tiny groups of atoms, or even single atoms, without any physical contact. It allows for incredible precision in studying them. It also led to super-sensitive measurement tools. This has huge interdisciplinary applications far beyond just physics. We suddenly got new ways to control and measure matter at its most fundamental level.
Can you give us some examples? For you, our listener, where might this pop up?
Sure, in medicine, these techniques could lead to much more advanced imaging. Non-invasive diagnostics. Imagine seeing biological processes at the molecular level with unprecedented detail.
That could revolutionize early disease detection, maybe.
Potentially, yes, or targeted drug delivery. In material science, it helps understand quantum properties at extreme cold, crucial for developing things like room temperature superconductors, the holy grail for energy transmission.
Wow. Okay.
Even in energy tech, maybe more efficient solar cells by better understanding light-matter interactions. And in chemistry, biophysics, a deeper understanding of molecular reactions, designing new catalysts, understanding how proteins fold. The list goes on.
It really spans the scientific landscape, but this kind of groundbreaking work, challenging fundamental constants, it rarely comes easy. What were some of the huge challenges Lene Hau and her team faced? Technically? Theoretically?
Oh, the technical challenges were just immense. First off, reaching and maintaining those near absolute zero temperatures for the BECs. That requires extreme precision with laser cooling, magnetic traps. You're trying to keep something colder than deep space, stable enough to manipulate with more lasers.
That's incredibly delicate.
It is. Even tiny environmental disturbances, a slight vibration, a stray magnetic field from elsewhere in the building could completely ruin an experiment days or weeks in the making. Schneppat's essay hints at the sheer grit involved. It demands unparalleled control.
Yeah, theoretically.
Theoretically, modeling these complex light-matter interactions in that quantum regime with EIT and BSEs, it demanded totally new approaches. The existing models just weren't enough. They had to solve incredibly complex equations.
Years of work, perfecting the apparatus, refining the theory.
Exactly. It's a testament to incredible perseverance and ingenuity.
And I imagine her ideas weren't just instantly accepted, were they? Slowing light,
Yeah.
stopping it. That must have faced some pushback.
Oh, absolutely not instantly accepted. Not at all. The initial skepticism was intense.
Why? Just because it was so radical?
Precisely because she was proposing to alter something considered a universal constant. When you challenge bedrock scientific beliefs, you invite pushback. It's natural, actually healthy for science. There were intense debates in journals, at conferences. Some questioned the theory, others wondered if it was just some technical artifact, some quirk of her setup.
So how did she convince them?
Through meticulous work. Flawless experiments, documented transparently, published openly. And crucially, her methods allowed others to replicate the experiments. And eventually, other labs did replicate it, validating her radical findings. That's what ultimately won over the community. The evidence became undeniable.
And overcoming all that, technically and socially within science, surely earned her major recognition.
Oh, absolutely. Her list of awards is long. It includes the MacArthur Fellowship, the so-called Genius Grant.
Ah, the Genius Grant, right.
Yeah, the Richtmeier Memorial Lecture Award. Membership in prestigious groups like the American Academy of Arts and Sciences, the National Academy of Sciences. But beyond the awards, she's also become this powerful inspiration, hasn't she? Especially for women in physics, a field still needing more diversity.
Yeah, that's a really important point.
She fosters new talent, promotes bold, unconventional thinking. Her career really shows that huge progress often comes from daring to question the unquestionable and backing it up with rigorous work.
So looking at the big picture, her lasting legacy, how does her work continue to shape science now and looking forward?
Well, her legacy is truly monumental. She didn't just make a discovery, she fundamentally shifted our view of light and matter. She popularized that revolutionary idea, light as a storable unit. That concept echoes through so much research today.
Like what specifically?
Ongoing research into making quantum memories more stable, last longer, become more scalable, integrating these quantum technologies with existing classical tech. And it keeps pushing fundamental questions about quantum mechanics itself. The nature of wave-particle duality, entanglement, how information behaves at the quantum level. Her vision really points towards, well, potentially sustainable new technologies and a future transformed by harnessing these quantum phenomena. It's an ongoing journey she helped launch.
What an incredible journey. We've explored the amazing contributions of Lene Vestergaard Hau. Her pioneering spirit really did expand the boundaries of what we thought was possible in physics. Her work, so clearly illuminated in that insightful essay by Jürgen Schneppat, it continues to echo, doesn't it?
Mhm.
Inviting new questions, inspiring future breakthroughs.
It really does. And her impact reminds us that this kind of foundational research, understanding the universe, it's not just academic curiosity. It provides the actual building blocks for technologies that will likely reshape our world in profound ways. From perfectly secure communication to computational power we can barely imagine right now.
It's a real testament to human curiosity and sheer ingenuity.
Indeed.
So, a final thought for you, our listener, to ponder as we wrap up. What new frontiers do you think Lene Hau's legacy, this idea of controlling light and matter at the quantum level, will inspire us to explore next? Thank you so much for joining us on this exploration. We hope you're as inspired by Lene Hau's story as we are. You can find more information about Jurgo Schneppat's work, including the essay we discussed, at schneppat.de. That's SCHNEPPPAT.DEDE. Goodbye for now, and keep curious.